Hello and welcome to this 18th session on symmetry in chemistry. Last time we looked at the diatomic molecule oxygen, indeed diatomic molecules in general, looked at its molecular orbital diagram, made sense of its photoelectron spectrum, and that also allowed us to understand the magnetism of oxygen because we had these unpaired electrons in the highest energy level state. What we're going to do this time is we're going to take it a bit further, looking at those unpaired electrons in more detail. And this should lead us to an explanation for the bizarre colours that we see. There's a red chemiluminescence we see in oxygen. Oxygen also looks blue in absorption in its liquid state. So our quest is going to be to try and understand all of that. And so what we're going to look at now, we're going to consider the whole molecule state of oxygen. So rather than just looking at individual orbitals and how they're occupied, considering the molecule as a whole. And so apart from those top two pi star orbitals, all the orbitals in the oxygen molecule are either completely full or completely empty. And actually this is the normal state of affairs in molecules. Virtually all molecules we come across, we find all the orbitals are either completely full or completely empty. And actually what you have in this situation is a zero net angular momenta. So all the spin angular momenta will cancel out, all the up and down spins will cancel, all the orbital angular momenta will cancel out from where all the orbitals are completely full or empty. It's like subshells in atoms. So where you have a completely full shell or a subshell in an atom, all the angular momenta, spin and orbital angular momenta all cancel out. But we have this special case in oxygen where we have these pi star electrons in the highest energy level where they're not spin paired, so the spins don't cancel out, hence the magnetism that's observed in oxygen. But what we're also going to have to do is we're going to have to consider how these electrons interact with each other. So the electrons are not just independent things in molecules. Actually what happens is the electrons all couple together, same thing in atoms. And so it turns out then that with this state in oxygen where we've got two electrons in the pi star level, and that's what we mean by pi star in brackets superscript 2. That superscript is the number of electrons, like you see 1s2 in atoms, for example. It turns out there are three possible energy levels that correspond to this, and so these microstates make this clear here. So you see those two blue boxes correspond to the two pi star orbitals. And so we see that on the left hand side we've got two electrons spinning parallel in the separate orbitals, and this is how we typically show the molecular orbital diagram for oxygen, with the last two electrons spinning up in the separate orbitals. But other ways we could draw the electrons, we could show the electrons anti-parallel in different orbitals, or indeed they could be anti-parallel in the same orbital, which we see on the right hand side. And then a little bit about the nomenclature. So the S there will be familiar as spin, so that we know the electron has got a spin half quantum number, and then we can think of that spin being projected as plus half or minus a half on the z-axis. And so in the left hand case we've got two spin plus halves combining to make one, and then in the other two microstates we've got anti-parallel spins plus half and minus half combining to give spin 0. And the capital S there denotes the sort of multi-electron state, the overall spin. What's more interesting perhaps is at the lower level, and so you can see we've got these two Greek lambdas. We've got the lowercase lambda plus or minus 1 under each orbital, and we've also got the capital Greek lambda on the right. And this is interesting because you see this actually corresponds to what we see in atoms with lowercase l and capital L. So you've met lowercase l before as the subshell quantum number. So this gives the orbital angular momentum of the different types of electron. One thing which you may not be quite so familiar with is that when you're combining electrons in an atom to consider the whole atom state, when you consider the orbital angular momentum of the atom as a whole, you're using capital L. So this idea of capital letters for multi-electron states and lowercase letters for single electron states, this carries over into the molecules with these Greek letters. So you remember that we had this idea of clockwise and anti-clockwise rotation, reflecting the sort of two-dimensional irreps. Well, this is what we see here with the pi orbitals. So of course remember pi is like the Greek for p, and a p orbital has got orbital angular momentum 1 quantum number. And so this lambda is plus or minus 1. This reflects the fact that the pi electrons have got a single unit of angular momentum, and it could be clockwise or anti-clockwise. These are the plus and 1 states that denote the two orbitals. Then the capital lambda there is what happens when you sum them together. So you see on the left-hand microstate and in the middle microstate on the screen, in both those cases, each of the two orbitals has got one electron in, an electron that you could call lambda plus 1 and an electron that you could call lambda minus 1. So when you sum those two lambdas together, you get 0. And that's why they're described as capital lambda equals 0. Whereas in the right-hand microstate, both of the electrons are in the same orbital, which we've labelled little lambda plus 1. And so when you sum those two electron lambdas together, you get capital lambda equals 2. And so, as I was saying before, we need to consider the electrons coupling together. And so actually the most important thing are these capital letter quantum numbers, which describe the coupled state of the electrons, because in reality, of course, electrons do couple, and we need to consider the overall state of them in the atom. So the next question is, we've got these three types of microstate that represent three possible energy states. What might be the relative energies of these states? What do you think is going to be the ground state? Well, that's perhaps slightly obvious, because we've seen already how in molecular orbital diagrams you tend to draw the two electrons spinning parallel and in separate orbitals if you've got two electrons in a doubly degenerate level like pi star. So we might assume then correctly that the left-hand microstate is the one that's lowest in energy. But what about the other two? What order do they come in? And then this final question on the screen, how is the Pauli principle relevant to these electronic states? So you remember what the Pauli principle is. The Pauli principle tells us that we can't have two electrons in a molecule or in an atom with identical quantum numbers. So what that means is we couldn't, for example, have two spinning up electrons in the same orbital, because they'd have identical quantum numbers, just like we see with atoms when we do electron configurations of atoms. Now, returning to the question about which of these energy levels is the most stable, we need to use Hund's rules to work this out. And actually, Hund's rules work just the same with atoms as they do with molecules. So on the screen, we've got the first Hund's rule. So the first thing we do is we look to maximise S. So by maximising the total spin quantum number, this means as far as possible having electrons spinning parallel. Obviously, if they're all spinning parallel, all of their spin angular momenta are summing together to give the largest possible S. So we maximise S, and actually this is why our ground state is indeed the ones with the two electrons spinning parallel, as we suggested last time. But then, of course, that did leave another couple of microstates, both of which had S equals 0, but they had different values of L. So how do we deal with different values of L? What's the relative energies of those? And so what we do is we take the largest value of L to represent the lowest energy. And so, this might seem slightly counterintuitive, because you might think, well, hold on, that's more orbital angular momentum. Doesn't that mean more energy? But in fact, I think the way to think about this is this idea that ultimately the electrons are trying to keep away from other electrons, because electrons mutually repel, and that if the L is maximised, so all the electrons have got the same L, that means they're all kind of rotating in the same direction. As if all the electrons are rotating in the same direction, they never have to cross each other's paths. They can all just go like round and round in phase. This is the kind of picture that we think of. And so with L maximised, the electrons never have to cross paths. I mean, that's a slightly kind of woolly argument, but it's kind of a way to appreciate what's going on. And so we decide then that the ground state of oxygen has capital S equals 1, electrons spinning parallel, and capital lambda equals 0. That's to say the electrons in separate orbitals. And so, of course, this tends to get translated into some quite tricky notation, spectroscopic notation, which looks even weirder with molecules than it does with atoms, as we get these Greek letters coming in. And so we've got this state here on the screen. Actually, the way you'd pronounce that, you'd pronounce that triplet-sigma G minus. And so that triplet there, that top left-hand superscripted 3, this is the spin multiplicity, which is 2s plus 1. where s is the total spin quantum number. And so actually what 2s plus 1 means, that's the total number of spin states you can have with capital S equals 1. And so basically that means that vector length 1 can be oriented as +1, 0 or -1. So those are the three different orientations or states of the spin that you can have. And so it gets called a triplet because it's triply degenerate. There are three, or at least there's three types of this spin orientation. Then looking at it in a bit more detail, since this is the product of multiplying together two electrons that are in pi g orbitals, then when you multiply pi g times pi g, one thing you can say is because those two orbitals have the same symmetry, what we always find when you multiply two identical irreps together is the result has to be fully symmetric. So in this case that would be a sigma g. And so you expect sigma g to crop up with a fully symmetric irrep, and also bearing in mind that looking at the parities, g times g with the two electrons, well g times g has to give g. So that gives us our sigma g there. Of course, I haven't yet explained what the minus sign is doing up there. There's the other one, what the minus superscript. So I think these minus superscripts, these relate to symmetry under a reflection plane. So this is anti-symmetric with respect to a mirror plane. Actually, this makes sense when you look at those orbitals. You can see them, reflecting in a mirror plane to give the opposite phases. But quite why we go for a minus in the ground state and not a plus, this is actually far from easy to explain. And so what it comes down to, actually, it's applying the Pauli principle. But actually this is quite a sophisticated treatment of the Pauli principle. I mean, normally when we look at the Pauli principle, we're just thinking about making sure that an electron doesn't have all the same quantum numbers as another electron. But actually we're up at a slightly higher level here. We're not looking at just the level of electrons. We're actually looking at these coupled states. And so applying the Pauli principle between coupled states involves this kind of slightly higher level of maths. Basically, it's harder work. So I'm not going to get into that here. But ultimately, this drops out of a Pauli principle consideration. Right, so that's our ground state. Now the first excited state. So this is looking at one of the other microstates now. So our first excited state, which is going to be a singlet state, because the electrons were anti-parallel, is going to be singlet delta G. And so the delta there, that's the one with capital delta is 2. So remember this is going to be lower energy than capital delta is 0 because we're maximizing capital lambda, I mean. So here we are, we get this notation singlet delta G. So again it's got to be G because this comes from the product of two electrons which are both G. Two orbitals which are both G rather. And then so the second excited state, so remember this is still pi star twice. This is the highest energy version that we saw, and this is where the electrons are anti-parallel but in separate orbitals. So capital S is 0 and capital lambda is 0. And so this has to be a singlet state because of S being 0, and the Greek letter is sigma, which corresponds to capital lambda being equal to 0. It was delta before because capital lambda was 2. And it so happens that this one is sigma delta G with a plus. And again, this is the Pauli stuff which gives us this result. So there we go. Ultimately, that basic configuration of pi star 2 electrons turns into 3 of these coupled states. Ground state being triplet sigma G minus, first excited state singlet delta G, second excited state singlet sigma G plus. Right, now just looking a little bit more about these degenerate orbitals and the Pauli principle, just looking at this in a bit more detail, because of course with these two electrons they're either going to give us capital lambda is 0, sigma state, or capital lambda 2, which is a delta state. And we remember from our character tables that the sigma state is singly degenerate and the delta state will be doubly degenerate, but this is clockwise or anti-clockwise. And because we've got two electrons, they could in principle either be triplet when they're spinning parallel or singlet when they're spinning anti-parallel. So I mean, on the basis of this argument, we'd expect to see more states than we do. And so we've got a little calculation here. So because we've got 2 of these sigma states, this accounts for the first 2 brackets. We could perhaps have 2 triplet states, so 2 times 3 for triplet, and times 1 because it's sigma. Then there's the other 2. We could have 2 singlets times 1 because it's sigma, and then also the delta state. That could be 6 degenerate, 3 times 2, 3 if it's a triplet, 2 because it's delta, or it could be a singlet, 1 because it's a singlet multiplied by 2 because it's delta. And if you multiply those up, add them all up, you get 16 possible states that you might expect just based on considering the orbital and the spin terms. What's interesting actually is that we do see all 16 of these states if our 2 electrons weren't in the same set of pi star orbitals. So if you could have 2 sets of pi star orbitals, let's say, if you had 1 electron in each, then you wouldn't have a Pauli problem, because the electron that's in the bottom 2 orbitals could be in any 4 of the spin orbital states, like you've got 2 orbitals times 2 spin states, and the other electron in the, let's say, the higher pair of pi star orbitals could also be completely independently in any 4 of the states. 4 times 4 is 16, gives you the 16 possible states. So actually we would see 16 possible states, or at least in terms of all the degeneracy, the total degeneracy of 16, we would see that if we didn't have a Pauli problem, and we wouldn't have a Pauli problem if they were separate pi levels. But in our case, because the 2 electrons are in degenerate orbitals, so it's the same pi star level with 2 orbitals in, one way we can think of it, of applying the Pauli principle, is saying, well, we've got 4 spin orbitals, so as I say, 2 orbitals times 2 spin states, and so how many ways can we assign 2 electrons to 4 spin orbitals if the order isn't important? So that's 4 factorial over 2 factorial 2 factorial is 6. And so 6, this is the degeneracy that we observe. Yes, we do have only 3 energy levels, but don't forget that the triplet state is 3 degenerate with spin, and the delta state is 2 degenerate with orbital angular momentum, plus or minus 1. And so adding those all together, you do actually have a total degeneracy of 6. We observe 3 energy levels, but there's a total of 6 possible states. And actually you can kind of unweave all the degeneracies by putting it all in a magnetic field. And so I think you would in principle see all 6 states, all 6 separate energy levels if they were in a magnetic field. But in the absence of a magnetic field, we just see our 3 basic levels. So there we go. Here are the microstates again, just to illustrate that. Right, now this is getting slightly more involved, and we've got this lovely picture on the right showing these different oxygen states. And so you can see at the bottom there, we've got these labels for our 3 energy levels. We can see triplet sigma G minus, singlet delta G, and singlet sigma G plus. But rather than just a level, we've got the whole kind of potential energy curve. And so what this is, on the x-axis, you've got the internuclear separation. And so this shows the fact that ultimately you're in a kind of potential well, where we can consider the nuclei stretched apart or pushed together. And so where you are in the bottom of the potential energy well, this would be the equilibrium internuclear distance. This is at the bond energy that we'd measure, the most stable bond energy. And curiously enough, if you look at the y-axis, actually the 0 in energy isn't level actually with the very bottom of the bottom curve. It's actually just slightly up from the bottom where you see a line. This is called the 0 point energy. So one of the curiosities about this is that the system actually can't get right to the very bottom of the well. So one slight problem is if you do get to the very bottom of the well, where you're sitting like at a perfect equilibrium internuclear distance, the problem that you'd have there is that your system, the particles, you would know precisely where they were. You'd have a very well-defined distance, and they'd be at the lowest energy state, so there'd be no need for them to be vibrating, for example. And so you'd actually end up with, you'd have a well-defined energy. So if the energy and the position and, by implication, the momentum were all infinitely known, you'd actually be in contravention of the uncertainty principle. So the uncertainty principle actually doesn't allow you to get to the very bottom of the well. but it forces you to be just a little bit higher. And when you're a little bit higher there, you can see there's a little bit of uncertainty then in the internuclear distance, which is, the length of that line. Right, so we're representing these states as these wells. And so as you can see here, as you start pulling the bond apart, ultimately, of course, you break the bond. And this is why I can see on the right-hand side, that line doesn't just keep going up and up and up, but eventually at a critical energy, it kind of goes horizontal. And this is where you've broken the bond, and that line, as it extends out, that's just the atoms flying apart from each other. So that energy that you can see up there is about 40,000 wave numbers. That energy is actually going to break the oxygen molecule in two altogether. And as the molecule breaks in two, it ends up as two oxygen atoms. And so you can see there that line at about 40,000 wave numbers, it's labelled with O, so that's just the oxygen atom, brackets 3P, or triplet-P I should say. And so this actually represents the ground state of oxygen. So you see the P there, similar sort of idea. This is where you've got the 3p orbitals, and you can think of them as having angular momentum 1. And you remember that 1, if you like, that vector length 1, can be oriented at +1, 0, -1. We're going to have 2 electrons. Actually, no, of course, you've got 4 electrons in oxygen. So of those 4 electrons, 3 of them go spin parallel in each of the p orbitals. The 4th one pairs up with one of the other electrons, and that leaves 2 unpaired electrons. And so actually, a bit like we saw with the oxygen molecule, it's the unpaired electrons which are the really important ones, because paired electrons, you're looking at really cancellation of angular momenta. So when we look at the unpaired electrons in oxygen, those 2 unpaired electrons give us this triplet state, where those 2 halves for these plus halves for the spin parallel electrons add up to give capital S equals 1, and that leads us to this 3 superscript, the degeneracy 2s plus 1, the spin degeneracy, and the capital P there. This is, if you like, the total sum of all the orbital angular momenta. So obviously there's lots of cancellation in the electrons, so it actually acts rather like just 2 electrons on its own. So if you consider the 2 unpaired electrons, if you had like 1 in the orbital that's +1 and 1 in the orbital that's 0 for the projection of the L vector, then they would give a total L of 1, which translates into P when you give these term symbols, just like it would have done, like it would have turned into pi in a molecule, for example. So there we go, and we've got our 3 separate energy levels giving 3 separate potential energy wells. So this is the sort of core information, let's say, in this diagram. And so our 3 levels that are associated with the pi star with 2 electrons in are those 3 collected at the bottom. But one thing we do see on the screen is we do see an energy level way above that in energy. So you can see up at around 50,000 wave numbers there. There is a different energy level, and so this is going to be corresponding to a sort of properly excited configuration. And so this is the next bullet point here. So in the properly excited configuration, what you're doing here is you're taking one of the pi electrons from the completely filled pi bonds, and you're promoting it up to the pi star anti-bonding orbital, because you see pi star was only had 2 electrons in, and there's room for 4 electrons in there. And so what you do is, when you promote an electron up, that means that you've got now 3 electrons in the pi star level, which is pi G symmetry, and then in the pi bonding, those 2 pi orbitals but below, they've now lost one of their electrons. There's a hole in there. And so actually what we see in the pi star above and the pi below, both of them in this excited state will have this pi hole in there. There'll be 3 electrons in each one. And actually having like a subshell or whatever, a group of orbitals, if they're full but with 1 gap in there, that 1 gap rather behaves like as if there were just a single electron in that level. And so ultimately in our excited state we're going to have pi u times pi g. So pi u and pi g are the irreps for the bonding and anti-bonding pi levels. And in fact, remember, in both levels we're just going to have a hole, 3 electrons in a hole, and that hole is going to act like a single electron. So it's rather like we had before with the 2 electrons in the pi star. That was pi times pi. And now we've got an electron promoted. The excited state is pi times pi. But there's 2 crucial differences. Firstly, one of our pi's is pi u, and this is because it's a bonding as opposed to an anti-bonding. And secondly, because the pi's are different from each other, we don't have the Pauli restriction. And so we've got 4 spin orbitals at the top, 4 spin orbitals at the bottom. Each one we can think of having an electron in it. Well, really it's a hole. And so we actually have, there's no restriction now in which states the electrons can occupy within their 4 spin orbitals. And so you get your 4 times 4, 16 possible states. And so the list here puts them all, gives them all. So what you get is you get the singlet and triplet version of the 3 levels we saw before. The difference is that rather than being G's, they're U's because of this, G times U multiplication. And so what we see at the top here is that this particular level up there, you can see on the diagram, is triplet sigma U minus. And that's one of our possibilities that we get from our excited configuration. And you can see that when this one dissociates, it dissociates to give different products. Yes, it still gives 2 oxygen atoms, and one of the atoms is triplet-P, but the other atom is singlet D. So in the singlet D case, what you've got is, because it's singlet, that means capital S is 0, that means all the electrons are paired. So in that case, you've got the 4 electrons in the 2p subshell of oxygen come as 2 pairs. So we can consider 2 pairs in the Ml plus 1, and 2 electrons in the Ml plus 1, 2 electrons in the Ml equals 0. And so when you sum all these projections of the L vector, it comes to plus 2, and that translates into D in spectroscopic notation. A bit like the D orbital was N equals 2. So that's quite interesting. And also we see that we've got a triplet plus a singlet product. And so I think that is allowed when we start from a triplet starting material. We haven't sort of violated a spin quantum number. And so one point I just make, another curiosity, is that even though we've got 16 degeneracy of the excited configuration, of course that doesn't mean 16 levels, because many of these are multiply degenerate. So for example, that triplet sigma U minus, that's 3-fold degenerate. But we've got all these levels here, so we've actually got 6 possible levels. You can see the notation for them on the screen. And it so happens that of those 6 levels, only one of them, this triplet sigma U minus, only one of them is bound. That means to say that you actually get a proper potential well with a minimum in it, where the molecule can sort of sit in that minimum, and the minimum represents the equilibrium internuclear distance. So what happens with all the other 5 is that rather than, you just get a line, a bit like a sort of exponential decay. It starts off at high energy on the left when the atoms are jammed together, and it just decays down and down and down, and it never actually gets to a minimum. Ultimately, it just plateaus out to the dissociated oxygen atoms like we have above. So that's the curiosity there. So there's actually only one possible bound state, it so happens, in that excited configuration. Now we get into the real business part. So what we're going to do is we're going to use this picture that we've been looking at, this picture of all the electron configurations of oxygen, to try and make sense of the chemiluminescence. So you can see one thing I've not mentioned yet on the diagram is that these 3 energy levels at the bottom, which are the 3 different energy levels associated with the pi star twice configuration, we can see the energy differences being marked on the diagram in terms of wavelength. So 762 nanometers is the wavelength that connects the second excited state to the ground state, and 1268 nanometers there is connecting the first excited state with the ground state. So of course obviously the wavelength is inversely proportional to the energy, that's why it's a bigger number lower down. And next to that we've got the lifetime of the state. So you've got 7 seconds at the top. I mean, that might not look very much. I mean, that is actually a very long time. for a spectroscopic transition. Normally expect lifetimes to be absolutely tiny, just a tiny fraction of a second. And then we have this absolutely gargantuan 45-minute lifetime. This is a very rare thing to see. So there's something seriously getting in the way of that singlet delta G state decaying back to the ground state. It's got a 45-minute lifetime. So we're going to look at this now in a little bit more detail. And so this relates to the beautiful red light that you get when you make singlet oxygen. So singlet oxygen means an excited state of dioxygen, the molecule, where you don't have the two electrons spinning parallel in the pi star orbital, but instead they're paired up to make a so-called singlet state, capital S equals 0. Now, of course, normally when you make oxygen, you just form oxygen in its normal ground state. And, of course, we typically make oxygen in the lab from hydrogen peroxide. And in the hydrogen peroxide molecule, all the electrons are paired. Now, how do we normally make oxygen from hydrogen peroxide? Well, typically add a catalyst, won't we? A transition metal catalyst. I think what happens is when the transition metal catalyst gets involved, with all of its shuttling electrons around, you end up with these kind of radical species of oxygen, which ultimately can combine to give you this oxygen radical. I mean, oxygen's a diradical really, isn't it? Because it's got two unpaired electrons. And so through the kind of normal catalytic mechanism that we see, it does allow for the formation of these radicals. What's interesting though is if you make oxygen a different way. And so you can see the equation on the board there. Here we're oxidizing hydrogen peroxide with chlorine in the presence of alkali. And so here we're making oxygen as one of the products. And actually when you get into the mechanism, what you do is you actually end up chlorinating the hydrogen peroxide to make chloroperoxide as ClO2-. And of course in this species all the electrons are paired. And so the way we make oxygen from this is that we're going to eliminate Cl-. And of course this involves a movement of a curly arrow. It involves two electrons and an electron pair moving. And so ultimately in this reaction we make oxygen through species where all the electrons are paired the whole time and electrons only move in pairs. And so that means when we make the oxygen atom through the sort of conservation of spin, I suppose, ultimately the oxygen has to have all of its electrons paired, and so we make singlet oxygen. And we produce singlet oxygen in its lowest energy state for singlet, which will be singlet delta G. So this is the first excited state above the ground state of oxygen. And so when you make that excited state of oxygen, you would expect it to relax, to decay back to the ground state. But there's something special about this transition. It's what you might call triply forbidden. It breaks 3 of the selection rules that are used to describe these electronic transitions. So we're going from a singlet state to a triplet state. So that means the spin of the molecule has to change from 0 to 1. Now that is something that a photon of light can't do. A photon of light can't carry away spin or add spin. Certainly not with light atoms in a first approximation. So it kind of breaks the spin rule. Then when you look at orbital angular momentum, the delta state it starts with, that's total orbital angular momentum 2, and then it's going to a sigma state, which is total orbital angular momentum 0. Now a photon will carry a unit of angular momentum, but this transition requires 2 units of angular momentum to be carried away. So it's also forbidden from the point of view of angular momentum. Orbital angular momentum, I should say. And the third way it's forbidden actually is to do with parity. So you can see that the singlet delta G and the ground state, the triplet sigma G minus, these are both even parity. But the whole process of an electric dipole transition and a photon of light being given off, these involve the electric dipole operator, which is itself an odd parity vector. And so a G to G transition like this is also forbidden. It has to be G to U or vice versa. So there are 3 different reasons why this is forbidden, which presents like a massive obstacle to this thing emitting light. And because of this massive obstacle, it is a very, very slow process. it has to kind of find a way to get around all the selection rules. And in fact, yes, it does find a very clever way of doing it. And so what it does is it recruits a second molecule. And so two molecules kind of hold hands and do the transition together. And this is a way it can kind of get around the selection rule. Because you see, in the product state, where we've got capital S equals 1, if there are two molecules kind of touching each other, I use this sort of expression, holding hands, if two molecules kind of get together, what they can do is, you can, a bit of a sort of crude analogy, but if you think of it as like one molecule with its spin pointing up, S equals 1 pointing up, and the other molecule sort of orients itself with its S equals 1 pointing down, and they kind of give each other a hug, then when the two come together, it's a bit like their spins are almost cancelling. And so with two molecules kind of getting up close and having their spins anti-parallel, it might look a little bit like a system with no net spin. And and you can use a similar argument about the orbital angular momentum. And so when two molecules kind of get together and cooperate in this way, we have this so-called two-body process. And this kind of gets around the selection rules. But we have got this very, very long lifetime here. Now, when you do the two-body process, when they get together, it means then that what happens is a single photon carries off the energy for two of these decays. And so one molecule dropping down is 1268 nanometers. But when two do it simultaneously, because it's two molecules involved, it's double the energy, so it's half the wavelength. So it goes down to 634 nanometers, and 634 nanometers is in the red. And so we see this amazing red glow when, if you bubble chlorine gas through cold alkaline hydrogen peroxide, you get this phenomenal red glow, this light, chemiluminescence so-called. And it actually comes from this remarkable process of forcing the oxygen to be produced with its electrons paired. So it's in a singlet excited state. It can't decay according to the selection rules. Two molecules come together, cooperate, double the energy, and it takes it into the red. So that's this remarkable process. And actually it's the same thing going on with liquid oxygen. So if liquid oxygen is going to absorb energy, absorb photons, again, it's a forbidden transition, triply forbidden. And so the way that the cold oxygen absorbs light is through this same two-body mechanism. And of course, in the liquefied form, the molecules are very, very, they're basically touching each other. So it's that much easier to have a kind of two-body process like this in the liquid form. So we can see then that the blue colour of liquid oxygen and the red colour of oxygen chemiluminescence actually involve the same mechanism and the same transition, but we're just doing it the other way around. So of course that energy gap, that corresponds to red light that we see with the chemiluminescence. But of course with the liquid oxygen, you're absorbing that red light. And of course when you absorb the red light, what you observe is the complementary colour. You see those frequencies which are not being absorbed by the molecules, and that leads to this blue colour that we observe with liquid oxygen. And finally now, getting onto the electronic spectrum of oxygen. So the previous spectrum we looked at was the photoelectron spectrum. So photoelectron spectroscopy, in a way, it's fairly simple because all you're doing is taking an electron out of the molecule altogether. But in the electronic spectrum, it's different. So what we're doing here is we're just going to excite an electron from one level to another level within the molecule. We're not actually ejecting the electron altogether. So here's the spectrum on the screen there. And so if you see on the x-axis, we've actually got wavelength on the scale. So actually the energy will increase from right to left. Obviously the highest energies have got the shortest wavelengths. And so you can see above, and so what we're doing is we're starting off with the molecule in the ground state, and we're absorbing some light energy, and we're seeing these absorptions when we form particular excited states on the molecule. So the first excited state on the molecule you're going to get on the far right. So on the far right we've got the lowest energy, and so the lowest energy transition that we do is taking us from our ground state up to the singlet delta, the first excited state. And there you go, there's that number 1268 again. And so this involves, as I say, so this will be a forbidden transition, and it just involves one photon taking the oxygen up to the first excited state. And it's got this at 0, 0 underneath it. And so the 0, 0 there, this represents the vibrational levels. We looked a bit at vibrational levels when we did the photoelectron spectrum. So the 0, 0 means that the ground state and the excited state are both in their bottom vibrational level. Neither are vibrationally excited, and that's the lowest energy. But the second peak there, it's the same electronic transition. You're going from the ground state to the first excited state, but this time the excited state also has a unit of vibrational excitation. And so that unit of vibrational excitation is going to be the difference in energy between those two states. So that extra bit of energy that's gone in has made the excited state vibrationally excited as well as electronically excited. And then you can see the next peak along, that little one, which is labelled 2, 0. Again, this is the excited state with 2 quanta of excitation of the bond vibration, so it's doubly vibrationally excited. Then, moving along, we get to the second excited state, which is the singlet sigma G+. And so we've got that first level, which is a 0, 0, so neither vibrationally excited, and then just to the left of that, we've got a fairly small peak there, which is the 1, 0. This is where the excited species, the singlet sigma G+, has a quantum of vibrational excitation. These two peaks kind of stand out, don't they? Because they also appear to have some extra structure to them, whereas the other peaks in the spectrum just look like simple peaks. And so my guess is that this may be something to do with rotation as well. So of course, as well as vibrating, molecules can also rotate. So we've already seen a vibrational spectrum superimposed on an electronic spectrum. The rotations tend to be much smaller energy gaps, and so again these are just like these like little details that add on. And so where you get a vibrational spectrum with little extra fine structure on, that's often a rotational level. So it's not very easily resolved, but that bit of extra kind of structure or broadness may well be something to do with rotational levels being excited. And then next one along, we get another different type of peak. So the peak at 630 there, 0, 0, this peak is labelled as singlet delta G, singlet delta G. And the reason it's got two of these terms attached to it is because this actually relates to a 2-molecule process, a 2-body process. So what's happening is we've got 2 oxygen molecules both being simultaneously excited to the singlet delta G state, and it happens with a single photon, so it's a 2-body process. And then the next one along has got this 1, 0 next to it. So that's essentially saying that one of the 2 oxygen molecules, I think, will have an extra unit of vibration, has an extra quantum of vibrational excitation. And then the next little peak along has a 2, 0 with this 2 quanta of vibration. So it's not, I wouldn't be totally sure if those 2 are on the same molecule or if it was one of each. I don't think it would make any difference to the energy actually, because whether it's singly or doubly excited, it's the same sort of unit of vibrational energy. Then going along, we've got another one of these double excitations, but this time one of the molecules goes to singlet delta G, the first excited state, while the other one goes to singlet sigma G+, the second excited state. That's this peak at 477, and there's actually a minuscule one after that. I've just added on with a pen, showing the vibrationally excited one. And then the final one on the left there, this is when 2 oxygen molecules are both getting excited to the second excited state, singlet sigma G+, and so you can see there's 2 vibrational versions of that, the 0, 0 and the 1, 0. So yeah, a lot going on in that spectrum. And so that's the point about molecular rotation. Another point of interest about this spectrum is that this spectrum was recorded at high pressure, 150 atmospheres. And so I think this accounts for the fact that we do see significant amounts of these 2-body absorptions. I think you wouldn't see this at atmospheric pressure. But obviously at high pressure, you're jamming the molecules close together, you're more likely to get effects that require the molecules to be very close together. And this is an interesting little calculation you can do. You can actually work out what the distance is between molecules just given the pressure. So you see, in this case we were given 150 atmospheres of pressure, and we can perhaps assume it's at room temperature. So you can use the old ideal gas equation, PV equals nRT, and because we're looking at the level of individual molecules, what you might do is, rather than looking at it as a molar equation where n is the number of moles and r is the molar ideal gas constant, what you can do is you can translate it into a per molecule equation. So that would be PV equals what you might call capital N, which would be number of molecules rather than number of moles, and then the molar ideal gas constant R would change into the Boltzmann constant K, which is the same thing but at the atomic level. So what you can do is you can rearrange that equation. So if you've got like PV equals capital N KT, you can rearrange that equation so the subject is V over N. And so this would be the volume divided by the number of molecules. And so that will give you the volume per molecule. So the V over N, the volume per molecule, equals K, Boltzmann's constant, multiplied by T, temperature in Kelvin, divided by P, the pressure. And so well, we'd be converting the pressure into pascals, and we can put those numbers in, and the volume that we get, we can think of that volume as being like a little cube. So of course if you take the cube root of that, that gives you the length of that cube. And if you imagine that each volume has got like a molecule in the middle, then the distance between two molecules on average will be the length of one side of that cube. So if you work through those numbers and you do that cube root, it does indeed come out as 0.65 nanometers. And what's significant about that is look at the wavelengths in the spectrum. So the spectrum involve wavelengths of hundreds of nanometers, and if the atoms are so close together that they're just under a nanometer between them, the way I like to think about it is, as far as the photon of light is concerned, it's just like a little dot, these two molecules together. So the two molecules, the dimension of the molecules and the distance between the molecules is just nothing compared to the wavelength of light. So it's almost as if the light can kind of deal with them both together. And of course, this is taken to an even greater extreme in the liquid, where the molecules are basically touching each other. And so that goes to show why, as I say, in the high pressure gas and also in the liquid state, these things are particularly evident, these two body processes. And as I say, the other thing I should say is that when we were doing the work with the singlet oxygen gas, that was all done at very low temperature as well. So while the temperatures are very low, that I suppose shuts off options for the molecules kind of dispersing their energy in other kind of non-radiative senses. And so it forces it more to emit their energy with a photon. So I think while the system is much hotter and there are many more collisions between molecules, and molecules maybe have got a bit more vibrational and rotational excitation, all of these things allow for a kind of non-radiative decay of the energy. And so, as I say, when we did this in practice in the lab, we have the reagents really cold. And so that, as I say, kind of shuts off some of the non-radiative alternatives and really forces it to do chemiluminescence. So basically, if the whole thing's done at room temperature, you don't really see proper chemiluminescence because it can use these non-radiative pathways at its disposal. But you cool it right down and then you definitely see the chemiluminescence. So I think that's quite a nice kind of combination of a rather beautiful experimental phenomenon with some rather lovely theory that draws it all together.